Swayam Prabha. Digital India. Educated India.
Hello everyone. In the previous class, we discussed about the elastic analysis of circular tunnels. We saw that how the stress distribution can be obtained all around the tunnel periphery or along any direction, say theta equal to 0 and theta equal to 90 degree. We saw these things with respect to hydrostatic state of stress as well as for uniaxial state of stress. So, today we will continue that discussion, and now we will see that how the displacements can be obtained in this elastic analysis of circular tunnel, because it is not only the stresses, but the displacements are also very important from the design point of view. So, today we will learn about the aspects related to the determination of displacements all around the tunnel periphery. So, these expressions can be obtained by integrating the stress displacement equations for plane stress state. Let us see how. So, for the plane stress state, we have these equations which are del u del r, which is equal to 1 upon E sigma r minus mu sigma theta, equation 1a. Then we have another equation which is u upon r plus 1 upon r del v del theta, that is equal to 1 upon E sigma theta minus mu times sigma r, 1b. Then the next one is 1 upon r del u del theta plus del v del r minus v upon r is equal to 2 1 plus mu divided by E into tau r theta. We discussed that this u is the radial displacement and v is the tangential displacement, which is in the direction perpendicular to the direction of u. Now, recall our discussion of the previous class. We had equation number 12 where the expression for sigma r, sigma theta etc. were given. So, whatever were the expression for these quantities which are here, sigma r, sigma theta and tau r theta, let us substitute it in these three equations, that is 1a, 1b and 1c. So, we have here substituting from equation number 12. So, first let us see that what will happen to this equation 1a. This is going to be del u del r will be equal to 1 upon E, and please substitute the expression for sigma r, which was 1 upon 2 Sx plus Sy 1 minus a square upon r square plus half Sx minus Sy 1 plus 3a to the power 4 upon r to the power 4 minus 4a square upon r square cos of 2 theta. This will be first term of this equation. Then minus mu upon e. Then substitute the expression for sigma theta, which is 1 upon 2 Sx plus Sy 1 plus a square upon r square minus half Sx minus Sy 1 plus 3a to the power 4 upon r to the power 4 cos of 2 theta. Make this equation as equation number 2a. Now, if we integrate this equation 2a, we will be getting the expression for u. Let us see how. So, integrating this equation 2a, what one can get? U is equal to 1 upon e half Sx plus Sy will remain as it is, and the term will be r minus will become plus, that is a square upon r. Simple integration with respect to r, plus half Sx minus Sy r minus a to the power 4 upon r cube plus 4a square upon r into cos of 2 theta. So, this will be one term minus mu upon e half Sx plus Sy r minus a square upon r minus half Sx minus Sy r minus a to the power 4 upon r cube into cos of 2 theta, and there is going to be one constant of integration which will only be the function of theta. So, make this equation as equation number 3, where this g1 theta is the constant of integration. Now, you substitute this equation number 3 and expression for u in equation number 1b. So, what we are going to get is this substituting equation 3 in equation 1b. So, we have here that as u plus del v del theta, that is equal to r upon e sigma theta minus mu sigma r, and this can be written as del v del theta is equal to r upon e sigma theta minus mu sigma r minus u. Now, here you again substitute the expression for sigma theta and sigma r and also for u, and then simplify it further. Let us see what we get. So, we have here delta v delta theta is equal to r upon e, that is half Sx plus Sy 1 plus a square upon r square minus half Sx minus Sy 1 plus 3a to the power 4 upon r to the power 4 into cos of 2 theta. This is one term minus mu r upon E half Sx plus Sy 1 minus a square upon r square plus half Sx minus Sy 1 plus 3a to the power 4 upon r to the power 4 minus 4a square upon r square into cos of 2 theta, that's another bracket. And then you have to write the expression for u which you just obtained, which is minus 1 upon E, that is half Sx plus Sy r plus a square upon r plus, I continue here in the next line, half Sx minus Sy r minus a to the power 4 upon r cube plus 4a square upon r multiplied by cos 2 theta, and this bracket will be closed now, and plus you will have another term mu upon E half Sx plus Sy r minus a square upon r minus half Sx minus Sy r minus a to the power 4 upon r cube cos of 2 theta minus g1 theta, which is the constant of integration. Although this is a very long equation, but have patience, this is very interesting. We are going to get something in a very simple manner. So, you just take the constant with respect to Sx plus Sy on one side and Sx minus Sy, and what you will get here is the simple form as 1 upon 2e Sx minus Sy into minus 2r minus 2a to the power 4 upon r cube minus 4a square upon r plus mu times minus 2r minus 2a to the power 4 upon r cube plus 4a square upon r cos of 2 theta plus g1 theta. You just need to simplify this equation, and this is what that you will get. Now, this del v del theta can also be written in this form, that is 1 upon E minus 2 Sx minus Sy upon 2 into r plus 2a square upon r plus a to the power 4 upon r cube into cos of 2 theta minus mu upon E. I am just rearranging these terms. R minus 2a square upon r plus a to the power 4 upon r cube into cos of 2 theta minus g1 theta. Now, if we integrate this equation, which is equation number 4, with respect to theta, I will be getting the expression for v. So, let us do that. Integrating equation number 4, what we will get is v is equal to 1 upon e minus half sx minus sy r plus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta. Please remember that here we are integrating with respect to theta. So, the term corresponding to r will remain as it is, minus mu upon e half sx minus sy r minus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta minus integration of g1 theta d theta plus g2 r. This is equation number 5, and this g2 r is again the constant of integration. Now, what we can do is differentiate equation number 3 with respect to theta and equation number 5 with respect to r. So, this is what that I am going to get is differentiating equation 3 with respect to theta and equation number 5, which is this equation, with respect to r. So, see, this is what that we will get, say del u del theta will be 1 upon e minus 2 into 1 upon 2 sx minus sy r minus a to the power 4 upon r cube plus 4a square upon r sine of 2 theta minus mu upon e 2 into 1 upon 2 sx minus sy r minus a to the power 4 upon r cube into sine of 2 theta and then plus d g1 theta d theta. That is what that we are going to get. So, mark this equation as equation number 6. And the other equation we have to differentiate with respect to r. So, this is what that we are going to get is 1 upon e minus half sx minus sy 1 minus 2a square upon r square minus 3a to the power 4 upon r to the power 4 sine of 2 theta minus mu upon e half sx minus sy 1 plus 2a square upon r square minus 3a to the power 4 upon r to the power 4 sine of 2 theta plus dg2r dr. I know that these are the long expression, but they are not difficult. I suggest that you do it patiently. I am giving you all these steps here in detail. So, you will not have any difficulty. Now, what we will do is, we will substitute these equations 5, 6, 7 in equation number 1c. So, substituting these equations 5, 6 and 7 in equation number 1c. So, what we are going to get is this 1 upon r into 1 upon e minus sx minus sy r minus a to the power 4 upon r cube plus 4a square upon r into sine of 2 theta, this bracket close, minus 1 upon r mu upon e sx minus sy r minus a to the power 4 upon r cube sine of 2 theta plus 1 upon r dg1 theta divided by d theta plus 1 upon e minus half sx minus sy 1 minus 2a square upon r square minus 3a to the power 4 upon r to the power 4 sine of 2 theta minus mu upon e half sx minus sy 1 plus 2a square upon r square minus 3a to the power 4 upon r to the power 4 multiplied by sine of 2 theta plus d g2r upon gr, then 1 minus 1 upon r into 1 upon e minus half sx minus sy r plus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta plus mu upon e into 1 upon r, and then you will have half sx minus sy r minus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta plus 1 upon r integration of g1 theta d theta minus 1 upon r g2 r. That is what that we are going to get, and this whole thing is going to be equal to tau r theta, which was there from equation number 12c. So, what was that? That was 2 into 1 plus mu upon e into minus half sx minus sy 1 minus 3a to the power 4 upon r to the power 4 plus 2a square upon r square into sine of 2 theta. So, this is what was tau r theta from equation number 12c. Now, what we need to do is, as we did in the case of the stress distribution, we compare the terms on either side of these equation. So, this is what that we are going to get. See, this all these terms, they have Sx minus Sy in with their terms. So, these terms, that is this one and this one, these have to be equal to 0 in a combined fashion. So, if I compare, so comparing the terms on either side of this equation, this is going to give us d g1 theta d theta plus integration g1 theta d theta. So, I write g1 theta term in one bracket and g2r term in another bracket. So, that is r d g2r dr minus g2r, and this will be equal to 0. This is equation number 8. Now, as this g1 theta is a function of theta only and your g2r is the function of r only. So, separately this and this, they both will be equal to a constant. So, that is what that we are going to write, that is r d g2r dr minus g2r, that is going to be a constant. Say that constant I write as k, and so make this equation as 9a. Then you have d g1 theta d theta plus integration g1 theta d theta. This is also going to be a constant, and I say that it is k. This is 9b. This is 9a and 9b. So, if we try to solve these two equations, what we are going to get from this 9a, this is going to be g2r is equal to cr minus k, say that is 10a, and 9b is will give us g1 theta will be equal to a sine of theta plus b cos of theta, that is 10b. These a, b and c, they are the constants to be determined from the boundary conditions using the boundary conditions. So, let us see further what we can do. So, this 10b I will substitute in equation number 3. So, substituting equation 10b in equation number 3. So, what we will get is u equal to 1 upon e, that is half Sx plus Sy r plus a square upon r plus half Sx minus Sy r minus a to the power 4 upon r cube plus 4a square upon r into cos of 2 theta minus mu upon e half Sx plus Sy r minus a square upon r minus half Sx minus Sy r minus a to the power 4 upon r cube into cos of 2 theta plus I will have here a sin theta plus b cos of theta. This equation I will mark as 11a. So similarly, I will substitute equation 10a in equation number 5, which is the expression for v. So we will get 1 upon e minus half Sx minus Sy r plus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta minus mu upon e half Sx minus Sy r minus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta and plus a cos of theta minus b sine of theta plus c into r. Now this is coming because of that g2r is only the function of r and therefore the term k is not written here. Now after getting this, it's the time to apply the boundary conditions. So we need to apply here the boundary conditions with respect to the displacement. So what do we have here is that displacement v will be equal to 0 when theta equal to 0 or pi by 2 for all values of r. Now what is the reason behind this? It is due to the axis of symmetry. So this is due to axis of symmetry. Now this v will be equal to 0 at theta equal to 0. This is going to give me a plus c into r equal to 0 and v is equal to 0 at theta equal to pi by 2 will give us minus b plus c into r equal to 0. And if you try to solve both of these equations, so the solution will be a equal to b equal to c equal to 0. Now like we did in case of the stresses, in this case also we will take the two conditions, one for the biaxial and the second one is for the uniaxial. So for the general biaxial state of stress, what we will get u as 1 upon e half Sx plus Sy r plus a square upon r plus half Sx minus Sy r minus a to the power 4 upon r cube plus 4a square upon r into cos of 2 theta minus mu upon e half sx plus sy r minus a square upon r minus half sx minus sy r minus a to the power 4 upon r cube cos of 2 theta. This is going to be 12a. So, similarly, you will have an expression for v as this 1 upon e minus half sx minus sy r plus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta minus mu upon e half sx minus sy r minus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta. That's 12b. Now, what will happen at the tunnel boundary? So, at the tunnel boundary, that is at r equal to a, just substitute r equal to a in the earlier expressions. So, you will be getting u equal to 1 upon e sx plus sy into a plus 2 times sx minus sy into a cos of 2 theta. This is equation number 13a. And v will be equal to minus 1 upon e 2 into sx minus sy into a sine of 2 theta. This is 13b. Now, you know that any point on the periphery will be defined by theta. If you just recall this figure that we had, so for any point we had this r comma theta, this was x direction and this was y direction, r was this distance and theta was here. So, along the periphery any point will be defined by the value of theta, because r is going to be equal to the radius of the tunnel, which is equal to a. So, for a typical hydrostatic state of stress, what will happen? Hydrostatic state of stress, that is Sx is equal to Sy is equal to minus P. Why I am writing minus P here? Because tension we have taken as positive in this case. So, this is compressive, so with a negative sign. Substitute this whole thing here and what you will get, u is equal to, see, this is minus 2Pa and this will become equal to 0. So, this will simply be minus 2Pa upon E. And what will happen to this term? This will become equal to 0. So, your V will be equal to 0. Make it equation number 14. Now, this is typically for the hydrostatic state of stress. Now, what will happen in case if you have the uniaxial state of stress where you have Sx equal to 0 and Sy is non-zero. So, you will get here as u equal to Sy upon E, that is A minus 2A cos of 2 theta. This is going to be equation number 15a, and similarly you will get V as Sy upon E that is 2a sine of 2 theta, equation number 15b. Now from here you just find out this term ue upon sy into a, that is going to be equal to 1 minus 2 cos of 2 theta. And from here if we obtain this expression ve upon sy into a, this will become 2 sine of 2 theta. Now the variation of this quantity and this quantity with respect to theta has been shown in this figure on the tunnel periphery, that is when you have r equal to a. That is what is the case that we are considering. So accordingly this plot is giving you the variation of u, and this one is giving you the variation of v. So just keep on substituting the value of theta from 0 to 90 degree and you will be able to generate this kind of a smooth curve. Some typical values which you can take, let us say that when you have here theta equal to 15 degree. Just substitute theta equal to 15 degree and see what you get. The value of v, it will work out to be 1. Similarly for theta equal to 75 degree also this v will work out to be 1, and this for 45 degree your u will work out to be 1. So this is how you keep on substituting the value of theta in these expressions and you will be able to get this variation of the displacement u and v on the tunnel periphery. Now let us see that what happens in case of the plane strain. So this is what that we discussed till now was the plane stress state. Now what will happen in case of the plane strain? Displacement which is occurring when the circular hole is subjected to a two-dimensional stress field under the condition of the plane strain. So in this case now we have to integrate the stress displacement equations which are there for the plane strain. In the previous case we integrated the equations for plane stress. Now from the theory of elasticity, what are the equations for the plane strain? See, these look like this: del u del r is equal to 1 upon E 1 minus mu square into sigma r minus mu times 1 plus mu into sigma theta. That is equation number 1. Then u upon r plus 1 upon r del v del theta is equal to 1 upon E 1 minus nu square sigma theta minus mu 1 plus mu sigma r, equation number 2. And then you have the last equation as 1 upon r del u del theta plus del v del r minus v upon r is equal to 2 1 minus mu divided by E into tau r theta. That is equation number 3. So these are the equations for stress displacement relationship for the plane strain situation. Now we can substitute the expression for sigma r, sigma theta and tau r theta again as we did in the previous case. So let us see what we get is del u del r will be equal to 1 minus mu square upon E half Sx plus Sy 1 minus a square upon r square plus half sx minus sy 1 plus 3a to the power 4 upon r to the power 4 minus 4a square upon r square cos of 2 theta, and the next term is minus mu 1 plus mu upon e half sx plus sy 1 plus a square upon r square minus half sx minus sy 1 plus 3a to the power 4 upon r to the power 4 cos of 2 theta. This is equation number 4. Similarly, you will have u upon r plus 1 upon r del v del theta as 1 minus mu square upon e half sx plus sy 1 plus a square upon r square minus half sx minus sy 1 plus 3a to the power 4 upon r to the power 4 cos of 2 theta minus mu 1 plus mu by e half sx plus sy 1 minus a square upon r square plus half sx minus sy 1 plus 3a to the power 4 upon r to the power 4 minus 4a square upon r square cos of 2 theta. Please do it slowly and carefully. Equation number 5, and the last equation, which is 1 upon r del u del theta plus del v del r minus v upon r. This is going to be minus 2 1 minus mu upon e half sx minus sy 1 minus 3a to the power 4 upon r to the power 4 plus 2a square upon r square into sine of 2 theta. Equation number 6. So now if you integrate these equations, this and this, you will be able to get the expression for u and v. How? Let us see. So u will be equal to 1 minus mu square upon e half sx plus sy r plus a square upon r plus half sx minus sy r minus a to the power 4 upon r cube plus 4a square upon r into cos of 2 theta minus mu 1 plus mu upon e half sx plus sy r minus a square upon r minus half sx minus sy r minus a to the power 4 upon r cube cos of 2 theta. This equation will be your equation number 7. And what will be the expression for v? Let us see that. This is v is equal to 1 minus mu square upon e into minus half sx minus sy r plus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta minus mu 1 plus mu upon E half Sx minus Sy r minus 2a square upon r plus a to the power 4 upon r cube into sine of 2 theta. This will be your equation number 8. Now these equations 7 and 8, these are the generalized expressions for u and v. U is the radial displacement, v is the tangential displacement, and you can see that these are the function of a, r, theta, sx, sy, mu and e. If you recall, in case of these stresses, those expressions were not the function of the elastic properties, but in case of the displacement, E and mu also come into the picture. Now, what happens at the periphery of the tunnel? That means at r equal to a. So, at periphery of the tunnel, what does that mean? That is r is equal to a. U will be equal to 1 minus mu square upon E into a Sx plus Sy plus 2a Sx minus Sy cos of 2 theta, that is equation number 9, and v will be equal to minus 1 minus mu square upon E 2a Sx minus Sy sine of 2 theta. This is equation number 10. Now, if you compare these two equations of the plane strain with those of the plane stress equations, so compare. And if I just substitute mu equal to 0.25, then we will see that u and v for the plane strain situation, they are approximately equal to 0.94 times the u and v for the plane stress case. So, in case if you have the elastic ground conditions, so tunnels do not require any support lining. They are stable. If the excavation is at shallow depth, then in this situation seismic effect plays an important role. So, as far as the expressions for displacement are concerned, we saw these for the plane stress as well as for the plane strain condition for a circular tunnel, and we see that when we compare these two, they are more or less of the same order for say mu equal to 0.25. to 5, and this is how the analysis of the circular tunnel can be carried out. So, we discussed about the not only the stresses, but the distribution of the displacement or the variation of the displacement all along the tunnel periphery, which is circular in shape. So, this is what that I wanted to discuss with you as far as the elastic analysis of circular tunnel is concerned. In the next class, we will discuss about the elastic analysis for the lining of the tunnel. Thank you very much.